Hi everyone, welcome again. So last time we mainly talk about mean difference from scratch, and we have calculated the pool defect size measures using the fixed defect meta-analysis, and we have actually calculated everything by hand. And finally, we have implemented the meta-count function from the meta package, and we have seen our calculated pool defect size, the confidence intervals, the z statistics, and the p-value were exactly the same as you get from the package, from the meta function, so the meta count actually. So for today, I would like to extend that to standardized mean difference. So we will calculate full standardized mean difference and from scratch. And the basic idea behind calculating standardized mean difference is like you assume, if you remember from our depression, this data. So you assume the measures of this depression data set. So you assume the way each study measures depression is different. So if you assume the studies the way they are measured is different, if you find out one study measures with Hamilton and the other one measures with a different depression scales, then the way you cannot combine them with mean difference. That will be erroneous because you cannot compare one study from the other to the other. So the only way you can make them comparable or possible to synthesize or to pull them together is using standardized mean difference. That is the basic idea behind. And the way you calculate the standardized mean difference is you simply calculate the mean difference, and then afterwards you simply standardize them by dividing the pooled standard deviation. So that's how you calculate standardized mean difference. This is really the basic standardized mean difference. So you have the mean in group 1 divided minus the mean in group 2 divided by the pooled standard deviation. I have already shown you how you calculate the pooled standard deviation, and let me just so this is how you calculate the pooled standard deviation. We will use this formula to calculate our standardized mean difference, and then this is not for this. We will use the corrected effect size measure. Last time, if you remember from my last tutorial, if you remember, I was talking about correcting effect sizes using H, especially if sample sizes are small. There was at one point that I was talking about. So this is effect size. No, I need to scroll somewhere. So there you go, here. So the way this is HSG, so you calculate standardized mean difference the way I have shown you in the formula, and then you multiply that with 1 minus 3 divided by 4 n minus 9. So this n is the total of the sample size in the control group, and so you basically add them and you divide them, and you just multiply that value with the standardized mean difference. So if the sample size is actually big, if it is big, this number will be so really tiny. So that means it will be 1. So it will exactly be standardized mean difference, and the HSG will approximately be the same. But if the sample size is small, then this HSG value will make sense. Will make more effect. It will be smaller than the small standardized mean difference that you get directly from calculating this using this formula. And so this is the way you calculate the standardized mean difference. This is just because I'm replacing the equation. Oh, sorry. Markdown is so the way you calculate your standardized mean difference is you subtract the mean 1 minus the mean 2. That means the experimental group minus the control group divided by the pooled standard deviation. This is a pooled standard deviation, and times the correction, this H's correction, this H's factor. Then you get the HSG. Once you get that, the pooled standard deviation is, as I have already shown you, it's already here also in this equation. And the other thing we need is variance of standardized mean difference. The variance of standardized mean difference, actually there are 3 different ways of calculating the variance of standardized mean difference. Some people calculate it this way. So in one, remember the difference in these equations I will show you. So this GK is a HSG. If you use HSG, they say you have to, that means a number in the control group. I mean, this has to be the total actually, NEK. So that means NEK plus NCK, that's the total. Just as we see it here, N1 plus N2 minus 2. There are anyway 3 different ways of calculating the variance of the standardized mean difference. So this is 1 here, so 2 times N1 plus N2 minus 2. This is the same standard mean difference, and this part of the equation is also the same. And again, NK means N1 plus N2. And again here it's different, so it's like 2 NK minus 3.94. So that means 2 N1 plus N2 minus 3.94. Instead of 2, they are suggesting to use minus 3.94. And again, the other one is that's the relatively the simpler one. This is the one that we are going to use today in this video. So that will be 2 times N1 plus N2. And that's what this is the value, the standardized mean difference that we use. And to calculate the standard error, as usual, it's just the square root of the variance that will give us the standard error. This value we will need it to calculate the confidence interval. And let me now attach the data. So to attach the data, I again will use the same data. In the future, I will have another data to use. But again, for now, I will have to use the same suicide prevention data that we have seen last time. And let me just run it and give you a quick look how that suicide prevention data set looks like. And I have already also converted these equations in R function. So I have this pooled, and also the variance is already there. So this is how the data looks like. So you have the author, you have the n in the experimental group, and the mean in the experimental group, standard deviation in the experimental group, and the same for the control group. And also you have like the publication here, the age group. So if you want to do like subgroup analysis, subgroup meta-analysis, you probably need these ones. And then at the end you have the control group. So now I already have the pooled standard deviation. I already changed them in a function. and the variance is also there. So the way we calculate, I'm choosing this easiest part of the equation, this one. To be honest, they don't make much difference. If you have a large sample size, if your sample size is large, then you don't have to worry, because this correction is -2, -3.94. They will not really make much difference, because they will be too small, so the effect will not be that big. But again, it's your choice which one to use. I prefer to use, but there should be a reason actually which one, and depending on your sample size. So you can choose whatever you would like to implement. So now we already have the pooled standard deviation function and the variance function. The first thing we need to do is I need to calculate the mean difference. The way I calculate the mean difference is let me just call the data, and let me just call it the mean difference, and then the mean difference will be calculated by the mean in the experimental group. The mean in the experimental group minus the mean in the control group. That will be the mean in the control group. Actually, this is making it complex. Okay, the mean in the control groups. Now I already have the mean difference. The next thing is I need to calculate my pooled standard deviation. I already have it somewhere. Maybe from the last time that I was demonstrating mean difference. This is actually what I need. So I will simply call this one. But for the variance, I will have to change it because it's a different variance formula. So let me run these ones here. So the variance requires N1, N2, and standardized mean difference, and this one requires N1, N2, SD1, and SD2, 4 different parameters. And so this one, the pooled standard deviation, I will get the pooled standard deviation. Once I get the pooled standard deviation, I will calculate the variance. For the variance, what I need is like N1, N2, and the standardized mean difference. But before that, I have to calculate. That means I have to calculate the standardized mean difference. The way I calculate the standardized mean difference is I need to use this suicide. Let me just. Oh, okay. Putting it wrong place. Let me remove this part of the equation because I put it in that line. So now let me calculate the standardized mean difference. For that, standardized mean difference is calculated by, first I need to calculate the mean difference. I already have the mean difference. So then let me see the standardized mean difference. So that means first I need to calculate standardized mean difference, and then I will multiply it because I would like to have the G, H's G. So I can create actually H's factor as an equation and then put it there. So that will be the simple standardized mean difference will be divided by this one, the pooled standard deviation. So that will get me the, let me make it weight, this one. We keep it aside so that it has to be, anyway, the suicide mean prevention mean difference will be the mean in the experimental group minus the mean in the control group, and the pooled standard deviation is, this is how it should look like. And then finally I have to add this H's factor. Maybe I can create an equation for it actually, so a function actually. So for that maybe I can, because I already did it for my. So that's how I calculate the H's factor will be NK. The NK will be actually not NK. Let me just N1, N2. Let me change it to N1, N2, and this will be 4 times. Otherwise, I can also create NK. It's okay. The NK would be the total of. It's just to make the equation less complicated. Otherwise, because I have too many brackets, I may make an error. So that means okay. So let me run this, and then the next thing is let me create that NK. Suicide prevention NK. So let me just create that NK. NK. That means the total number of people in experimental in the control group means NK plus, in the control group plus that one here, that guy, and NC. So now I can use this H's factor. So now I have the NK, that means the total sample, and the suicide prevention, and mean difference will be calculated here, and I get the pooled standard deviation here. Once I get the pooled standard deviation, I can create my standardized mean difference. My standardized mean difference is the simplest one is calculated by the mean difference divided by the pooled standard deviation. But again, I have to use this H's factor. So for that, let me calculate this one here, and let me correct that standardized mean difference. Actually, let me call it H's G, and that will be calculated by standardized mean difference here times this H's factor, and the H's factor will get me NK. So I simply call my function H's factor here times H's factor as a function, and that will give me this value here. So the suicide prevention, the total sample size in a sense. So now I already have the G, and I can simply run this, and I will have the H's G value. After that, what I need is the variance, and then once I get the variance, I can simply calculate my weight, and once I have the weight, I can pool them, and that's how I proceed. So the pooled standard deviation is there. Okay. Now I have to run it. Hopefully it works everything, but I can also go back and run it and see. Maybe instead of loading, because if I load it, it will have to run it again. So that means I will have to rerun the whole thing again, because if I have to load it. So let me print it, and now I have to see what I have. So now I already have what I want. So the HSG is the standardized mean difference. It's really a small effect, so that means because depending on your sample size, if your sample size is actually the same, so you will not have that much impact. That the Hedges factor that we have seen here, that I have shown you here somewhere here. This is the Hedges factor, the Hedges correction. Especially if your sample size is small, it makes a difference. Otherwise, they are more or less the same. So you see, there is only a tiny difference. But of course, in the end, when you pull, they may make a little bit difference. But to be honest, when many people write standardized mean difference in publications, they mean HSG. That's because that's a standard in the meta-count function, in the metaphor also. They usually correct for that, because it doesn't matter if you apply correction. If the sample size is bigger, so that means the corrected the HSG and the simplest form of standardized mean difference will be the same. So it will not make that difference if your sample size is big. But if your sample size is small, then the difference will be high. So now I already have the pooled standard deviation, the standardized mean difference, the HSG. That's the G, the value we need to pool. Now the next thing is I need to calculate the variance. For the variance, I have already created that equation here, the variance. So for that, I will need N1, N2, and SMD. I already have the equation. The equation I already converted them in a function. This is the equation we need. So let me scroll down and see. So I need N1. This variance, the MAD, the standard deviation of the variance of the standardized mean difference, N1, N2, and SMD. So I don't need the other values, standard deviation and the like. So the other one I need is the standardized mean difference. So that's the G, actually the HSG. That's the value I need. So now, okay, don't know what is wrong. SD2 is missing. Okay, maybe I didn't run it. I didn't run this equation. No, did I? No, maybe I didn't. Okay, let me do it again. Now it should work, I believe. So variance MD, or maybe I have a different name. Oh yeah, okay, that's variance SMD. Yeah, it's variance for the standardized mean difference, HSG. Now I should be able to get my my variance. So if I go back and run this, I will have to see at the very end of my data, I will see my the variance. So now to pull, what I need is a weight, and the weight is the inverse variance. So that means I will simply take this and calculate something here. I call that the weight. Then that means it's the inverse variance. That's what I have. And I calculate the weight total. The weight total will be the summation of that inverse variance. So that will be the weight. That will give me the weight total. And if I want the standard error, that will make it square root of the weight total. 1 over square root of 1 over weight total. That will give me the standard error, because this value I need it for calculating confidence interval. So this will be, there will be one value, but then this one will be one value, but the other ones I will have the weight for each study. So if I calculate this and go back and print it, I will have to see I will need to see the weight here. So now I have the weight, but I need to calculate this in terms of percentage. If you want to calculate in terms of percentage, this is how you calculate it. So let me just maybe weight percent, let me call it weight percent, is actually the weight percent, and that will be summation of individual weight divided by the weight total, and times 100. That will give me the percentage value. Sometimes you see it in publication or in forest plots, people add percentage weights, but that's how you calculate the weight. And let me now go back and print that data so that I can see the weight. So this is the weight in percentage. So this study contributed 60%, 16% of the weight, and this one contributed 19.3, and then 19.2. Yeah, it was like that. These are the weights. But roughly everything we need to calculate our meta-analysis, we already have everything. So the only thing we are left with pulling effect size. So to pull our effect size, what we need is we have to calculate. I can go back and show you the last equation in my previous. So this is the way you calculate the mean. The mean is like the summation of x size divided by n, the total number of observations. But in this case, it's a weighted mean. For the weighted mean, you calculate the effect size by the weight. The weight is the inverse variance. We already have the inverse variance weight, and then divided by the summation of the inverse variance, or the weights. So now we already have everything. And now let me just calculate my pooled effect size. Okay, pooled standardized mean difference, let me call it that way instead. For the pooled standardized mean difference, so the first variable that I need is that HSG. So the HSG, I already call it HSG actually. So G, that's how I call it. If you scroll down and up, if I show you, this is how I call it. Now I have to multiply that with inverse variance. So that will be my weight, the weight of each study. So then, because this will give me, each study has a weight, so we have many weights. So if I show you here, we have all. Okay, I must have made some error. This computer is getting so slow. Yeah, okay, there you go. Now it should work. So now I have all these weights, but I have to multiply that with HSG, and I will have to sum them. I will sum. This PC is getting slow again. this S has to be small. And now sum suicide prevention HSG times suicide rate. Now once I have that, I can simply now divide by the total. So that means total number of weight. So the total we have seen here. Yeah, I put it here. Now I should be able to see my pooled standardized mean difference. Don't worry, we will see in our using the package, and we will compare whether our manually calculated pooled standardized mean difference is the same as the one you get using the package. So now, yeah, so that is my my pooled standardized mean difference. But if I want, I can put it in because this is long, so I can again this PC is getting busy. I probably have to pause it. Okay, it's getting busy. I don't know for some reason. So now we are back. Okay, so we have already our pooled standardized mean difference, but let me round it into 4 digits because that is a very long number. So I don't want to have that. Now let me. Now this is my pooled standardized mean difference. The next thing is I would like to calculate my confidence interval. So the way you calculate the confidence interval is the lower bound and the upper bound. Let me call the lower, and let me actually put it in round. And then for that, the pooled standardized mean difference plus 1.96, that is z alpha over 2 times standard error. The standard error is the one we already calculated here. That's the standard error here. That will be the lower bound. The lower bound will actually be minus, that's not a plus, and the upper bound will be the plus 1. And my round function, I have to round it to 4 digits, and the same is for upper bound. Upper. Now this one has to be plus, and I have to do it in 4 digits. Now let me put it lower and upper. Calculate lower, upper. Actually, the easiest would be I need to paste them. The pooled standard deviation, the lower and the upper. Let me just paste so that we see all of them together. Paste, pooled SMD, then the lower, and the upper. Now I should be able to to see everything. So now the pooled standard deviation, it tells us pooled is minus 0.34 divided, I mean the confidence interval is from minus 0.3475 until minus 0.21147. But the one thing remains, that is z-stat. The z-stat is calculated by the pooled standardized mean difference divided by standard error. Standard error, we already have that. And let me put it this way, maybe round it in again in 4 digits or 3 digits, and we will see how it works. There we go. Now we have our standard, I mean the z statistics is minus 3.89, and the pooled standard mean difference is here and again here. So now if we want the p-value, I mean we can see that it's not passing through 0, so that means our the pooled effect size is actually statistically significant. But we can approximately see the p-value in this z table. This is minus 3.89. This is one-sided p-value here that I will show you here. Minus 3.89. So minus 3.89 is here is about 0.0005. It's highly significant, but we have to. This is one-sided, and for two-sided we have to multiply this by 2. So that means our p-value would be 0.001. 1, 2, 3 zeros. The p-value is about 0.001. Actually 3 zeros. So that's our p-value. Now we have everything now. So maybe we can do it using the meta count function. So for the meta count, I already in my last tutorial I already show you how it is. So as this is, you use the meta count function, and then at the end you define the effect size measure. That's mean difference or standardized mean difference. So we will choose the standardized mean difference for today, for this session here, and then this one I will simply call it standardized mean difference. Now it should be yeah, standardized mean difference, and yeah, so bingo. So it's like, okay, minus 0.2311. This is what we calculated here. And minus 0.3475, that's the lower bound, that's what we calculated here again, and minus 0.1147, again, that's what we calculated. And then if we want the z-stat, minus 3.89, minus 3.819 to be exact, and the p-value is exactly as we calculated, 0.001, 3 zeros, and this is what we get. So that's exactly how we calculated it. Next time I will next I will talk more about pooling effect size using random effects meta-analysis, but you can also calculate these things manually, like I-square, the Q-stat, and these values. You can calculate them manually, exactly. But I mean, takes a bit of time. I mean, you see how much we pass through to reach this standardized mean difference, pooled Yeah, but it's just one. I mean, how many lines you can put this in one line and you have everything. That's actually the advantage of using a package. But sometimes it's nice to go what is happening under the hood and to understand how you actually pull studies, how you calculate the weight and the variance, the standard error, the pool standard deviation. Then if you know this, then well, the other thing will be easy, especially applying the package functions. They make it easy for you. But sometimes it's a good idea to practice things from scratch. Yeah, so that's how you calculate the standardized mean difference. In the previous session, I have already shown you how you calculate the mean difference. So for the next tutorial, I will show you how you do random effects meta-analysis. But until then, enjoy meta-analysis and please share and like this video. And that will be that will encourage me a lot to do more tutorials. This is just free. Whenever I have time, I simply jump in and do something. But I will continue doing more if you encourage me to do so. Thanks for today, and I hope we will see you again.